What's up, everyone? I never grabbed my phone. Shit. Oh, my phone alarm's going off somewhere in the house. All right, so let's get into it. First, I want to give a little bit of an overview. Oh, I didn't collapse a lot of these. Of where we're at. We got through, of course, the first 9 lectures. We're on lecture 10, which is the last lecture of content. What's up, Joey? What's up, Selman? So this is the last lecture of content that you're responsible for. After today's lecture, it's all out there on the table. You can complete the course. You can do all 8 programming tasks, of course, and you're ready for the next quiz, which is Tuesday. So the last 2 lectures, on Tuesday, of course, it's a quiz. It's a regular quiz at 11 a.m. Eastern Time. I'm going to email the 2 quizzes, the Classes 3 and Data Structures 3, which are polymorphism and graphs quizzes. And then at 12:15, just as usual, I'll go live, but there's no new content for that lecture, where the last quiz lecture was the opening files and getting you ready for task 6. There's no new content on Tuesday's lecture. I'm going to treat it as a homework help session. Hopefully y'all will come with your homework questions, anything that's tripping you up. I'll try to go over things that will specifically help you for the homework. Left to my own devices, if nobody has questions, I'll likely do a lot of debugger stuff. I'll just do like an hour and a half of debugger examples and showing you how to take broken code that's failing your test cases and go through the debugger to see all the information there and use that to help you debug. I want to go through task 8 before we get into today's content. We went over tasks 1 through 7. Last time I had some extra time, so we kind of cleaned up some of the homework introductions that I missed. So we'll introduce 8. So all 8 programming tasks have been introduced. They're out there. They're ready for you to do. The big thing with this one is degrees of separation. So that's what we want to do. So let's define what this is and figure out what it is at all. So we're using the movie data. We're not using any ratings for this one, but we are using the movie data itself of the title and cast lists, and most importantly, the cast list. We're going to start using that information for something more interesting than we have so far. We haven't really done anything with the cast lists except checking to make sure they're right while ignoring case. So what we want to do is code up this degrees of separation kind of game. I guess people call it a game, but finding the degrees of separation between 2 cast members in movies. So if we have, for example, 2 actors and they haven't been in a movie together, the question is, how many other cast members do you have to go through to be able to get from one to the other, where any 2 cast members are connected. It's hard for me to explain this without using graph terminology, which we're about to learn in the slides. They're connected if they're in a movie together. So, for example, in the data, if I want to find the degrees of separation between Chris Pratt and Kevin Bacon, which, mind you, the data is a little bit outdated. It's not absolutely current, and I'll explain that in a second. But if I want to find the degrees of separation between Chris Pratt and Kevin Bacon, according to our data, they have a degree of separation of 2 because they've never been in a movie together, but we can connect them through one other actor. So Chris Pratt was in Moneyball with Brad Pitt, and then Brad Pitt was in Sleepers with Kevin Bacon. So we can go Chris Pratt to Brad Pitt to Kevin Bacon. It took us 2 jumps to get from Chris Pratt to Kevin Bacon. Now, in reality, ignoring our data, in reality, Chris Pratt and Kevin Bacon have a degree of separation of 1 at this point because they were in the holiday special, the Guardians holiday special. They were in that together, so now they were in a movie together. Their degree of separation is 1. So that's what we want to find out. But given any 2 actors, what's their degrees of separation? And this is commonly used to find someone's Bacon number. That's their degrees of separation from Kevin Bacon. That's where this whole kind of game originated from. So how do we find that between any two actors given the data that we have? How do we manage that? How do we write code that's going to figure that out? That's our goal. And yeah, I give that warning. Just if you are using this, if you are actually interested and you want to like find people's bacon number, the data isn't going to give us the exact bacon number. Plus, I significantly trimmed down the data. A lot of movies that were in the original data set, I did remove just to keep the file size manageable, so your code doesn't take forever to run if you have slight inefficiencies in it. So if you do want to use this, you can go get the full data set. I think even that's missing some of the newer movies. I don't think they keep it updated to get the latest movies that like just came out. So just keep that in mind if you are like trying to one up your friend. No, that's not their bacon number. Look, I ran my code. You might be off by a little bit. You won't ever find a bacon number that's lower than the actual one, but you might be missing some movies and have a higher number than the actual number. All right. So with that said, that's our homework, finding degrees of separation. This is one of those homeworks, the kind of homework I really like, where it's a nice simple description. You got to find the degrees of separation between two actors, and most of this is just setup, what to name your classes, what the constructor should take, and all that stuff. But most of this is just notes on explaining degrees of separation a little bit further. What is degrees of separation? And if they're not connected, return -1. So if you can't find a path from one actor to the other, like if we want to find the degrees of separation between Chris Pratt and me, that's going to be effectively infinity. Our method is going to return -1 to say there is no connection between those two actors, because I've never been in anything. So let's get started on graphs. So we got quite a bit to cover. The way this is going to break down is the first slide deck is introducing what graphs even are and introducing what breadth first search is very briefly. The second deck of slides is all about breadth first search and how we're actually going to use breadth first search to solve that degrees of separation problem. This is going to tell you everything you need to do for the homework, and then a little bit extra, the bonus content I keep mentioning that was cut for the summer course. This slide deck will actually show you how to complete some of that bonus content, some of the extra homework that you could use to earn an A. This will show you how to do that. I'll explain what I mean by that, and when we get to those slides, and I'll tell you here's the line of stuff that you're not really going to need to know. I want to know why this always comes up. I want to say don't pop up ever. Like, I don't want any of this. AI prompts. Is that part of... Oh. No, I don't like this feature. I want to turn it off. I just told you I don't like it. I'm going to try quickly because it keeps coming up during lectures. And I want it to not show up. There we go. Okay. That wasn't too hard. All right. So this is going to tell you everything you need to do the homework, but we have to, of course, introduce what graphs even are first. And then graph example, this is one big old memory diagram. So this is going to show you what you need for next week's quiz on Tuesday for the Data Structures 3 quiz, which this is one, actually, I think this has been the case for quite a while, ever since probably Inheritance, that there's no new content for the memory diagrams. If you could do memory diagrams up until classes 2, you could do Data Structures 2, classes 3, and Data Structures 3. There's no new content, concepts, or anything. It's just, do you understand memory diagrams or not? So the memory diagram, I think, is less important. You already should be able to do the graph's memory diagram, even if I don't even tell you what a graph is. You should be able to trace through code that looks like this. It's all concepts that you've seen before. It's constructors, it's instance variables, it's method calls, it's references, and this. It's a hash map. It's just combinations of things you've seen already. So I maintain that, but I'll still go through the memory diagram just to give you a specific example of what that quiz is going to look like. And of course, according to the quiz results for classes 2 and data structures 2, a shocking amount of you still don't know how to do memory diagrams, unfortunately. So another example will be nice to get that out. So that's the roadmap of what we're looking at. Let's get right into... Oh, actually, there was one more thing. I wanted to do a rundown of the rest of the course. So I talked about what Lecture 11 is going to look like. Lecture 12, I'm not going live. This is 3 full hours. When you have the second chance quizzes for classes 1, 2, 3, data structures 1, 2, 3, all 6 quizzes, that's going to take a while. I'm going to give you the full 3 hours to do the quizzes. So if you're one of those unfortunate people in the situation where you need all 6 quizzes in order to pass the class, you got that full 3 hours, so you can spend the full half hour on each quiz. And then I'll tack on an extra 15 minutes at the end for the submission like I've done for the other one. So you have 3 hours to do the quizzes and then an extra 15 minutes. Wait, is that how it works out? It's not a full 3 hours though, is it? Because the lecture goes from 11 to 2:40 on the schedule. I've been doing it to 2:30 because I'm cutting the break, but I'll give you to 2:40 for the quizzes. And then maybe the submissions would have to be at 3. I think that has to be the case. Can someone tell me when 191, CSE191 starts? I think I'll have the submission deadline at the start time of that, so people in 191 aren't disadvantaged. That'll be the submission deadline. It's 1 hour. Then 15 extra. Oh, yeah, for the current quizzes. Yeah, I give you 1 full hour and then the 15 extra to submit. So I want to give you 3 hours plus the 15 minutes to submit. But I think I will definitely be running up against 191 at that point. So I don't want to do that. Starts at 2. All right, so I'll give... Thank you. Thanks, my spell, David. So I'll make the submission deadline at 2. Right? That makes sense, right? So you have a full 3 hours. It means you don't necessarily get the extra 15 minutes to submit. So if you are doing all 3 quizzes, you do get, unfortunately, a little bit less than 30 minutes per quiz if you take the full 15 minutes to submit. But that's, I don't see a better way of doing that. I'll have submissions due at 2. That's when submissions will close. Yeah, so, and that'll be on Gerline and myself, mostly Gerline, that will make sure that your classes 3 and data structures 3 quiz grades are done by Thursday. Hopefully before Thursday, so you know what you have to study for. We're going to get those, I'll say at the latest Wednesday night, we'll get those results out. So there won't be any lecture. The whole time will be just these quizzes from 11 a.m. Eastern time to 2 p.m. Eastern time. That's when submissions will close, is 2 p.m. Eastern time. So this means if you only have to do a few of these, most of you are in a situation where you don't have to do all 6 of them. So if you have like 1 or 2 to do, you'll still get the full 3 hours. So if you got 2 quizzes to do, take an hour and a half on each of them. Make sure, look it over, triple, quadruple check it. Make sure you got everything exactly the way it should be. You'll have plenty of extra time to do those quizzes. So everybody gets full 3 hours, regardless of how many of these quizzes you'll need. And then Friday, so next Thursday, last day of classes. This should say, I think I saw this earlier and I just didn't fix it. This should say Thursday, of course. Then on Friday at midnight, end of day Friday is when all the programming tasks are due. I plan to have extra office hours on Friday. So this day I'm going to have a small marathon. I haven't decided exactly when that'll be, but I'll have a small marathon of office hours. And be there available to help you all as you're finishing up these tasks. A lot of you are, I shouldn't say a lot, but a surprising number of students, I guess, actually, I shouldn't say surprising either because I'm not surprised by it, but a decent number of you are pretty far behind on the assignments. I mean, I'm rooting for you to get caught up, but I said last time, if you haven't finished programming test 4 by now, you're in a situation where I don't see you passing the class, unfortunately. But I'll be there to help you out if you do want to try to make that last effort and really push through to try to get them done. Especially if you only have like a couple tasks left. I definitely want to be there for you. Those of you who are finishing like task 8 at that time. A lot of you will be wrapping up task 8. I want to be there to help you, give you that one last push that you need to finish the assignment. Maybe there's one thing in your way that just doesn't mesh with my grader or something. You know, I want to be there for you to make sure you have the assistance you need. And those of you who are way behind trying to catch up, I mean, I'll give you a little help, but I'll probably most likely just be like, look, you're still on task 5. The deadline's tonight. Like I'm sorry. I'll give you 10 minutes or so, but you can't be this far behind. So that's what we're looking at on Friday as well. So that's what the rest of the semester is. We're at the end here. All right, and now let's get into it for real. Let's talk about what graphs are. All right, so we've talked about quite a few data structures already. Why even learn about another one? That's where I want to start. So we've talked about our sequential data structures. This was our array list, depending on what language we're using. JavaScript, I forgot what order I said them in. JavaScript, Java, or Python, I think is the order I said those in. And then we talked about linked list in Java. We built our own linked list and saw how that worked, how its references, each node has a reference to the next node, and each node has a single value in the list, as opposed to our other our array list or vanilla arrays, which were one continuous block of memory where these values are right next to each other in memory, so they don't need references to each other. It's just the next memory location. So these are sequential because order matters. These, regardless of which type, which flavor we use, the order does matter. So they're sequential. There is a clear sequence of these values. Then we had our key value stores. These, instead of being sequential and keeping track of things by the order that they're in, key value stores care about mapping keys, which can be any value, not necessarily integers, from 0 to size -1. Now we can have keys of any type and then map those keys to specific values. So this gave us a different way of representing information by being able to map keys to values. And the order didn't matter here. When we add these 3 key value pairs to our key value store, the order in which they're actually stored in can be different. If we're iterating over the keys, we're not going to get them necessarily in this order. And then we talked about trees last week. This was our first nonlinear data structure. So we're thinking about branching paths where we can take different paths through the data structure. And we took advantage of that branching feature to be able to get log n depth in the tree, which gave us log n runtime for our crucial insert and find. And in 250, you'll talk about deleting and doing extra other operations in log n time. Very nice, efficient data structure if used properly. Of course, we didn't use it properly in 116, but in 250, they'll show you how to use it properly with self-balancing binary search trees, which are, I think, a really cool data structure because you can get that log n efficiency, log n runtime. All right, so why even learn another one? We got all these data structures. Well, what if our data looks like this? This is a type of data that purposely we haven't used because we didn't really have a data structure to be able to work with it. So we have subway systems in New York City. We have different subway lines, and what we effectively have are subway stations that are connected by subway lines. So if you want to get from one subway station to another subway station, you have to find a path of connections, a path of lines that'll get you from point A to point B. And you'd use those connections and use those stations and connections to be able to get to where you're going. Same thing with intersections. We have intersections that are connected by roads. So we can get from one intersection to another intersection by traveling across a road. And these intersections are the points where multiple roads meet. So if I want to get from point A to point B, I want to get from UB to, say, Niagara Falls, I have to find a series of intersections and possibly transferring roads, transferring roads to be able to get from one intersection to the next intersection to the next intersection until I get to my destination. And finally, the one that we'll be using, since these ones have way too much data for lecture examples, the one we'll be using for the lecture example, this is the very early days of the internet. This, I believe, was when it was still ARPANET, where we have several locations which are connected by cables and can send internet packets to each other. So the early days of the internet, we have these locations that can connect to each other. And how do we send a message from SRI to Harvard? We have to find a sequence of these connections to be able to get that packet sent or routed through the internet, or the precursor of the internet here, from one location to another. So given our data structures that we know about, our sequential data structures, our key value pairs, and our branching nonlinear trees, how do we represent this data? And I think the closest one is going to be a tree, since we have this very nonlinear way of structure. This nonlinear structure to our data itself, let's use a nonlinear data structure to be able to represent that. So let's pick a starting point. I picked UCLA at random when I made the slide. And then all of its children, instead of just being a binary tree, let's make this a nodes able to have as many child nodes as they want. So UCLA is connected to Stanford, SRI, UCSB, and RAND. So let's have UCLA's child nodes be those nodes to which it's connected. Seems like a reasonable thing to do to start. But then when we get to Stanford or any of these nodes, we'll get to Stanford and do the same thing. Its neighbors are SRI and UCLA. So we got SRI and UCLA, and oh crap, we have duplicate nodes here. So Stanford's child nodes, what should be its child nodes, are actually nodes that are already in the graph. So we have SRI in the graph twice, which Stanford has really no chance of knowing that SRI exists in the graph. And UCLA, which Stanford could, we could have a parent reference in our nodes and have it look at its parent reference and make sure it doesn't backtrack like that. So we could possibly get rid of that, but SRI is going to pose more of a challenge of how we get rid of that. So all the child nodes are going to be repeated, and we're going to go infinite with this. Because SRI is then going to have UCLA as a child. UCLA will have Stanford as a child. We're going infinite if we use a graph. So let's try something a little bit different. Whenever we're going to add a duplicate node or a duplicate location, let's just not add it. And instead, we're going to add the connection to the existing node. So Stanford, instead of having SRI as a new child node, let's forget the idea of trees where everything goes down from the root and allow these connections to existing nodes. So Stanford can have a connection to SRI that exists in the node as a node that is connected to UCLA. Forget about UCLA being like the root of the tree and just treat this as a whole bunch of nodes that can just have references to each other, to any other nodes. And this is going to be our graph. And this is similar to the structure of a tree. In fact, trees and graphs in our code are going to be very different. We're coding them very differently. But in theory, trees and graphs in CS theory, they're very, very similar. In fact, a tree is a graph. It's a very specific type of graph in that it's a graph that doesn't have cycles. So a cycle is where you can get from one node to that node again without traveling backwards across an edge. I should say without repeating an edge. Without repeating an edge more than once. So we can get from UCLA to Stanford to SRI back to UCLA. That's a cycle in our graph. Trees cannot have cycles. So once we have this information, which is the struggle that we had representing this as a tree, once we have this cycle here, this cannot be represented using a tree. It is not a tree once it has a cycle. It is a graph. Now, our graph can be a tree. We can use everything we're going to see about representing graphs and just have a tree, have a graph that just happens to not have any cycles, and that would be a tree. But a graph is allowed to have these cycles. So we're allowed to represent information like this, or our subway stations, or our intersections. We can represent that information in this way. So since we can have these cycles, our tree algorithms won't work. So because you might be tempted to say, well, let me just have a tree with, instead of left and right references, it'll have an array list of all the references, and then that array list can contain references to nodes that are already in the tree, and I'll just use all my tree code otherwise for this. But what happens when you run a tree traversal? So we have our traversal, which would go through to all the neighbors and make all the recursive calls, and then make a recursive call, and then make a recursive call, and you're going to get stuck in the first cycle that you find. You're going to get in an infinite recursion. You're going to make infinite recursion calls, and if you're not tail recursive, you're going to blow up the stack and get your Stack Overflow error. So we can't use the same algorithms that we used for trees once we have these cycles, because our tree algorithms did work off of the assumption that we don't have cycles. So now that we have cycles, we got to rewrite our algorithms and work with new algorithms to work with our new form of data. There's no if null in this because every node is connected to other nodes. And I've already been using the word a bit. So let's talk about nodes and edges. This is how we're going to represent the data. We're no longer going to have a node. This is going to sound weird at first, but we're no longer going to have a node-based data structure with our graph, in the sense that we had a linked list node class and a binary tree node class. We're not going to have that anymore. We're going to have a graph class, and that one class is going to store all of the nodes and all of the edges, which are a connection between two nodes. And so the node still stores a piece of information just like they always have, but we're going to represent them in our code much differently than we did. We're not going to have a graph node class. That's not going to be a thing. We're not going to have a graph node class that has a list of all of its connections. We're going to put all that information in a graph class, which is on the next... Oh, I did forget. I was going to say, if I didn't forget, it's on the next slide. It's coming up, though. We're going to see the code soon. So to represent this graph, what we're actually going to use is a hash map or any key value store that's going to map each node to all of the neighbors of that node. That's how we'll represent our graphs. And those of you in 191 or have already taken 191, all of this is going to be review for the start for introducing graphs. First of all, but you should be learning about both adjacency lists and adjacency matrices. So an adjacency matrix is a different way of representing a graph that we're not going to use. It's where you have a matrix with all the nodes as rows and all the nodes as columns, and then you have either true or false or 1 or 0, something to represent if they're connected by an edge. We're not going to see that one in 116. We're only going to use adjacency list. So this is an adjacency list. And here's the code. So here's how we're going to do it in code. Here's all the good stuff. And we're not going to focus on the code too much until that third slide deck, which would be the Friday lecture in a regular semester of Monday, Wednesday, Friday. We'll revisit this code, but I do want to show it. We'll revisit the code for the memory diagram. But I do want to show it early just to show you kind of more concretely what I'm talking about with this. So we're going to have a hash map. First, we're going to use generics. So we're going to use generics so we can have a graph of any type. Our graph example here is going to be strings. Your graph in your homework is also going to be strings, isn't it? It'll be the names of the cast members. So those will be strings. Hint, I guess, if that's a spoiler, I guess. Uh, so we're going to have a hash map of values to an array list of values. So in our case, each string that represents a node, a node's value, is going to be mapped to an array list of all of its neighbors. So if I have this adjacency list with all of my graph information from this graph, if I say, hey, adjacency list, give me the neighbors of UCLA, it should give me an array list containing the strings Stanford, SRI, UCSB, and RAND. So when we create the graph, we're going to initialize our adjacency list to a new hash map. And I'm using this add bidirectional edge. Now, bidirectional edges are the only edges we're going to use in the homework. You might see, you will see non-bidirectional edge, so just add edge in the quiz, mostly just because it's less stack frames. I want to cut down the stack frames. So the memory diagram later in this lecture is only going to use add edge, not add bidirectional edge. And your quiz will also only use add edge, not add bidirectional edge. Add bidirectional edge is just twice as... actually, it's not too bad, is it? You know what? It doesn't even add a stack frame. Maybe I'll make the quiz like that. I don't know. Probably I'll make the quiz with add edge just because that's what the memory diagram is going to look like. It actually isn't an extra stack frame though. So add edge for your quiz, but add bidirectional edge. The difference is bidirectional edge, the edge can be traveled in both directions. So in our internet example, each edge, if I have a connection between UCLA and Stanford, that means UCLA can send packets to Stanford and Stanford can send packets to UCLA. For your homework, if two actors were in a movie together, they are both connected to each other. It doesn't make sense for one actor to be able to get to the other one with a degree of separation of 1, but not vice versa. Those are going to be bidirectional edges because they can be traversed in both directions. Our intersections, our subways, same thing. Maybe you can have a one-directional subway where the line just goes one way and then returns back to the beginning and goes one way, but we're not going to mess with that. So adding a bidirectional edge is going to add that edge to both adjacency lists. And before we add to an adjacency list, we're going to add those edges in both directions for the bidirectional edge to say that each of these nodes are neighbors of each other is effectively what we're saying here. Before we can do that, we're going to initialize the array list for each node. So initialize that node in the adjacency list with the add node method, which is going to lazily initialize. So if we don't have any entry in the adjacency list for this key yet, for this value, then add a new array list, create that new array list for that key. So if it's the very first time we've seen this node, initialize in the adjacency list, initialize it to a new array list. And then we can safely add to those array lists because we know they're going to exist. We know get of node 1, get of node 2 will not return null because we've added them, or won't give us a key not found error because we've already initialized them by calling add node first. So that's our graph code. That's all we'll need in the graph class. And then we'll write an algorithm. We're only going to learn one algorithm, I suppose, breadth first search, where we're going to work with this information. So there's going to be a get adjacency list method in here too. I didn't put it on this slide. You'll call get adjacency list after you add all your edges, and then work with that adjacency list to run your breadth first search and find your degrees of separation. Okay, the code will come back for the memory diagram. Let's introduce a little more vocab. We got some definitions to get out there. Not really I guess it is vocab, but definitions to get out there because I'll be using these terms throughout the lecture. A path is a sequence of nodes where each pair of consecutive nodes are connected by an edge. So this is a path in the graph because UCLA, SRI connected by an edge, Utah, MIT, BBN, RAND. This is a valid path in the graph because each pair of consecutive nodes is connected by an edge. So I can traverse this path with no issue. SRI, Utah, BBN is not a path. SRI to Utah, that's fine, but Utah to BBN, there's no edge connecting these two, so this is not a valid path. And this is what your adjacency list will look like in your code. So like if I say adjacency list.get rand, it's going to give me this array list with these 4 neighbors. And we can see that each edge is technically in the adjacency list twice, since these are bidirectional edges. So Stanford to UCLA and UCLA to Stanford, this tells us that they're both neighbors of each other. So no matter which node I ask for the neighbors of, we're going to get the other node. If I ask Stanford, what's your neighbors? It's going to find UCLA. If I ask UCLA, what's your neighbors? It's going to find Stanford. So I don't have to worry about going through my whole adjacency list to look for those neighbors. If I want all the neighbors of UCLA, here they all are. And breadth first search, the big algorithm that we'll learn. So the graph code is of course given to you. The breadth first search code is not given to you. Your task for the homework is to implement breadth first search and use it to extract the degrees of separation information. So first, before we even talk about degrees of separation, let's talk about a simpler problem that we face is how do we tell if a graph is connected? So a connected graph, or the connected component of a node, the connected component of a node is going to be every single node where there exists a path from that node to the other nodes. So UCLA's connected component, I can get to Stanford, SRI, etc., etc. I can get from UCLA to any other node in the graph. So the UCLA connected component is the entire graph. And when that's the case, we say the graph itself is connected, because we can get from any node to any other node via a path. But what happens if we change the graph a little bit? So I deleted 2 edges here, and now the connected component is, for each node, is a little bit different, and this graph is no longer connected. So if this is the case, how do we even tell if 2 nodes in the graph are connected at all? Well, we're going to need an algorithm for that. So let's start. Oh, actually we won't, because this one you can just look at it, you can figure it out. But the internet's a little bit bigger these days. We don't have just a handful of locations. We have crap tons. We have a lot of them. Just looking at this one, I can't tell if 2 nodes are connected, much less calculating the distance between 2 nodes, which I haven't defined yet. But figuring out how long it takes to get from this node to this node, or what's the optimal path between them, forget about it. It's not happening without an algorithm. It's not happening just visually looking at this thing. Not going to happen. So we're going to use breadth first search. For this, we're going to choose a starting node and then continuously explore the neighbors of nodes that have been explored. I don't know if that sense will make sense yet, but it will make sense in a bit. So I'm going to pick a starting node. I'm going to pick UCLA because it's right there on top, so why not? And then with breadth first search, we're going to explore all of the neighbors of the explored nodes. So UCLA, I'm going to go to my adjacency list and say, okay, what are all the neighbors of my starting node? And I'm going to explore all of those nodes. So this green box is my explored box. I've explored all these nodes. And then I'm going to explore the neighboring nodes of all the nodes that have been explored, which is the new nodes that have just been explored. So I'm going to go to my adjacency list, Stanford, UCLA, and SRI. Those have both been explored. SRI, UCLA, UCSB, Utah, and Stanford. So I'll find Utah. UCSB is going to find SRI, UCLA, and Rand. Those have all been explored, so I learned nothing new. And then Rand is going to find UCLA, UCSB, and SDC. So SDC is the new one. So I'm going to explore all the neighbors, effectively the neighbors of the starting node, then the neighbors of the neighbors of the starting node, then the neighbors of the neighbors of the neighbors of the starting node. So I'm going to go to Utah. It's going to find SRI and SDC. They've both been explored. And then SDC is going to find Utah and Rand. They've both been explored. So we're going to continuously repeat this process until we have a round where no new nodes have been explored. So when we explored the neighbors of Utah and SDC, we didn't find anything new. And we can repeat as many times as we want. We're not going to find anything new after that happens after a full round. So once we explore Utah and SDC, no new nodes are found. So we know we've found the entire connected component of the starting node. And all of these, no matter which node we start at in a connected component, we're going to get that same exact connected component. So we could choose UCSB as our starting node. We'll get the same result. We'll get this connected component. And if you wanted to find all the connected components of a graph, you would go grab a node that hasn't been explored and run the algorithm again and find the other connected component of this graph. So we have a graph with two connected components, and it's a non-connected graph. Which is, this slide I'm going to skip. This is a motivation slide. Like when this is a Monday lecture, this is how I motivate, get you all super stoked and pumped up for Wednesday's lecture. But we're about to do Wednesday's lecture, so I don't really need this slide. So that's breadth first search and finding connectivity. So if we want to find if two nodes are connected, we're going to run breadth first search starting at one of the nodes. And then if at any point through the runtime of the algorithm, finding that whole connected component of the first node, if we ever explore the other node, then we know they're connected. But if we don't, then they're not connected. So we can find if two nodes are connected at all. So that's enough to get you just the when to return -1 in the homework. We can figure out when to return -1 if their two actors are not connected at all. And I think I guess I haven't checked, but I would guess that all of the, I did check, but I forgot. All of the actors in the data that's given, I believe they're all connected. I think I removed all the data. If there was an actor who was just in one movie by themselves, I would remove that from the data. But you're expected to do the same thing you did in task 6 and 7. Tasks 6 and 7, where you're creating test files. You're taking a subset of those movies and creating your test case files, and then running your code, your degrees of separation, on these smaller files. So you can actually get the interesting cases where two actors aren't connected, where two actors have a degree of separation of 5, where two actors have a degree of separation of 1, and you can play with the data that way. So you'll be able to create test cases that have this feature. And of course, I have those test cases in Autolab. Your code's going to have to take care of those. Well, even with 15 minutes of intro, that lecture's a little late. Which is fine, because this one has a lot going on. So finding connected component, that's fine and all, cool. And that's something you'll likely talk about later in your computer science career, especially in CSE 331. That should come up. But what we're really interested in is degrees of separation. That's what you're asked to do for your homework, so let's find out how to find that degrees of separation. And like I said before at the top of the lecture, this is the slide deck that's going to show you exactly what you need to do for your homework. Students do fight me on that, have fought me in the past. You didn't show us exactly what to do, Jesse. I maintain that I do, but I only show you the theory. I don't show you exactly how to convert it to code, though I do give you some pretty heavy-handed hints in this lecture. So let's talk about our definitions. We talked about what a path is. Let's talk about the length of a path now. So if I have this path, Lincoln to MIT to Utah to SDC, Rand, UCSB to SRI, this is a path. It's a valid path. Those are all connected by edges. And the length of the path is the number of edges in the path. So this has 1, 2, 3, 4, 5, 6 edges. So this is a path of length 6. which is also equal to the number of nodes in the path minus 1. So I have 7 nodes in this path, subtract 1, that's also going to give you the length of the path. So whatever way you want to use to compute it. Distance between two nodes is the length of a shortest path between the nodes. Even in my slide I say the shortest path, but there can be multiple different shortest paths. Can I find an example quick? I guess this one. So Carnegie, there's a shortest path 1, 2, 3 to MIT, and then 1, 2, 3 to MIT. So there's multiple shortest paths to get to the same node. So it's the length of a shortest path, just in case there are multiple shortest paths. There can be multiple shortest paths, but the length of and then I mess it up. The length of a shortest path between two nodes is the distance between those two nodes. So we had that path from Lincoln to SRI of length 6, but there is a shorter path, 1, 2, 3. There's a path of length 3 connecting those two nodes. So the distance between Lincoln and SRI is 3. And try as you might, you're never going to find a path of length 2 or length 1 connecting Lincoln and SRI. 3 is the shortest path you can find. So the distance between them is 3. And if two nodes are connected by an edge, like RAND and BBN, then their distance is 1. The path from RAND to BBN is just go right from RAND to BBN. That's a path with one edge, two nodes. So that's a path of length 1, and you're not going to find a path shorter than 1. So that's the shortest path. So the distance between them is 1. The only way to get a path less than length 1 is if you're finding the distance from a node to itself. From SRI to SRI, the path is just SRI. 0 nodes, 0 edges, 1 node. So the length of the path is 0, and distance is 0 of a node to itself. So, if you built a graph, I'll say this again at the end. I have a few slides on it, but I want to make sure I'm very upfront about what we're talking about here. If you built a graph where each node is an actor, and each actor or cast member is connected to another cast member if they were in a movie together, then the degrees of separation between two actors in that graph is exactly the distance between their two nodes. So here I can get a more concrete, more well-explained definition of this degrees of separation. Build a graph where where nodes are actors. It could be a graph of strings where the values are the names of the actors. And there's an edge, add an edge between two actors if they were in a movie together. So go through your movie data and build your graph as you process the actors in each movie. And then the distance between two actors in that graph is exactly their degrees of separation. There's a 1-to-1 correlation between distance in that graph and degrees of separation. So the homework is really asking you to, 1, build the graph, given the movies data, given an array list of movies, and then find the distance between two nodes in that graph. When you're asked to find the degrees of separation between two actors, I'm asking for the distance between those two actors in that graph. Can you use dynamic programming in breadth first search, depth first search? If you want to. In 1.6, I'm concerned about why you're asking though. And it depends what you're calling dynamic programming. If I think about it, I think what I'm about to show you would be considered dynamic programming. Not quite. I don't know if I would or wouldn't. But, yeah, I'd question why you want to or what you really mean by that. I wouldn't stop you on the homework, but I would also be suspicious about why you're doing it. Unless you're doing it in the flavor that I'm about to show you. Then I'd be like, oh, you paid attention in lecture. Awesome. So how do we find the distance between two nodes? That's the task we're faced with. That's really, I'm not going to help you build the graph. I feel like that's pretty straightforward. It does pose some challenge. There are some challenges to it. but not overwhelmingly so. You have an array list of strings. You want to navigate through it, getting every pair of strings, and then adding that edge to the graph. And you already have the add bidirectional edge method. You already have the graph class. So it's calling the add bidirectional edge method on those pairs. Or depending on how you go through it, you could just call add edge as long as you're getting every pair twice in both directions, which isn't too hard to do if you have a double loop, nested loop. So building the graph, the only thing that's left once we have the graph is given two nodes in the graph, how do we find the distance between them? And we're going to use breadth first search. This is the big useful thing we're going to get out of breadth first search. There's nothing on the homework where I say what's the connected component or anything. We can already use it based on what I said to find if two nodes are connected at all. So if you should return -1 or not. But that doesn't really help too much. And the way I'm about to show you is going to implicitly figure that out as well, when to return -1. All right, so let's run through breadth first search. The last time I just kind of hand waved it and said, explore the neighbors of the neighbors. Da, da, da. I'm going to kind of hand wave this one as well. And then I'm going to run through breadth first search 2 more times. We're going to see 4 runs of breadth first search today, each with subsequently more detail. The third one is going to be the critical one for your homework. But of course, if you don't understand the first 2, you're not going to understand the third one. So let's run breadth first search again. And this time we're going to keep track of the paths that we take to explore each node. And I'm going to start at Carnegie this time because I'm sick of starting at the top every time. So we're going to start at Carnegie for this one. And when we explore the neighbors and the neighbors of the neighbors, etc., we're going to keep track of the edges by redrawing the graph using only the edges that we took. And each time we add a node, we're going to draw it visually lower than the previous node, the node that discovered it. So I'm going to start with Carnegie, and I'm going to draw it right up here, and then redraw the graph with only the edges that we used. So Carnegie is going to explore Case in Harvard. So in my graph over here, I'm going to redraw this graph using only the edges that that we're using to explore other nodes, and drawing them visually lower. So Carnegie discovered Case in Harvard. Case is going to discover Lincoln. Harvard is going to discover BBN. So I'm keeping track of the paths that I use to find each node. Carnegie to Lincoln, I use this path. Case to Lincoln. So I redraw that over here, but in a different way visually, even though it's the same information. But we're going to remove some edges. And I'm always drawing the nodes we discover lower visually on the slide. Now we have a situation here. Lincoln and BBN are both going to fight over MIT. When this is the case, we're going to choose an edge arbitrarily. I'm just going to say that Lincoln discovered MIT. Now in our code, this will be decided just by the order in our adjacency lists, and we'll see that in the next run. But for this one, I'm just going to pick one. I'm going to pick Lincoln to discover MIT just because it makes my graph over here look a little prettier, a little more symmetric. So Lincoln discovered MIT, which means BBN. We're never going to rediscover a node. If a node's already been discovered, we don't go discover it again. So when BBN sees MIT as its neighbor, it sees that it's already been explored and skips it. Likewise with Harvard. BBN is going to say, Harvard, oh, it's one of my neighbors, but it's already been explored. So I'm going to skip it. But when it sees Rand, it says, ooh, Rand, this is one of my neighbors that has not been explored. So I'm going to add it to my graph. I'm going to explore it. And coloring these in orange means that node has been explored. We've seen that node. We know about that node. Don't visit it again. Because if we start revisiting nodes that have already been explored, we start going infinite. We're going to get stuck in cycles, and nothing's going to work the way we want it to. All right, MIT is going to find Utah, and Rand is going to find UCLA, UCSB, and SDC. So we're going to add those, again, going lower each time. And then Utah, UCSB, and UCLA are all going to fight over SRI. I forget which one I chose. I think Utah. And then UCLA is the only one that gets to find Stanford. So UCLA is finding Stanford, and Utah is going to find SRI. And notice that there are some edges in this graph that were never used in our run of breadth first search. And those edges don't exist in our graph over here. So this is the same graph, same two graphs, except this graph has several edges removed, and we rearranged it visually. Because when we have a graph, there's no sense of like the root node of a graph. When I draw this visually this way, I just picked where each node goes. Like there's no rhyme or reason to it. How you represent a graph visually for like representing on a slide like this doesn't really matter as long as the nodes all exist and all the edges exist. There's no rhyme or reason to the structure. So I redrew it visually, but that doesn't change anything fundamental about the graph, except I did remove some edges, which does change the graph fundamentally. Okay, so why do we do this? Let's take a look at our graph that we're left with. This graph will always be a tree in the sense that it has no cycles. And it's got levels. So the way we drew each new node visually lower in this graph, or this tree, or this breadth first search tree, if you will, we can divide those into levels and number those levels. So we'll say Carnegie is at level 0, the starting node. Its neighbors are on level 1. The neighbors of the neighbors, the next round that we went through and found nodes, level 2. Next round that we went to and found nodes, level 3, 4, 5. And what's the point of all this? Well, that level number is exactly equal to the distance from the starting node to any node on that level. So the starting node to itself, distance 0. The starting node to its neighbors, distance 1. The starting node to the neighbors of the neighbors, level 2, etc., etc. So Carnegie to SRI or Stanford have distance 5. So to get from Carnegie to Stanford, or Stanford to Carnegie, since this is a bidirectional graph, is going to take 5 edges. At an absolute minimum, you cannot find a shorter path in this graph between those two nodes. It doesn't exist, because if it did exist, breadth first search guarantees that it would have found it. Breadth first search will find the shortest path, or a shortest path, from the starting node to all other nodes in the graph. So try as you might, Carnegie to Stanford is distance 5. You will never find a path in this graph shorter than 5. I can go 1, 2, 3, 4, 5. I can go 1, 2, 3. Actually, I think there is only one shortest path. SRI, it was also 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm never going to get shorter than 5. There are multiple shortest paths, but they're all length 5. So the distance between Carnegie and SRI, the distance between Carnegie and Stanford is 5 in this graph. Now that you probably could have found out, you could have stared at this graph for a minute or so and figured that out. But once your graphs are larger, once you have thousands of, I forget how many movies are in that file, but thousands of movies, thousands of actors, it's going to be a lot tougher to do just by looking through the data. You're not going to want to do that. You'll be able to write the code faster. So we want to write code that does this. That's the ultimate goal. It's a computer science course after all, right? We want to learn about the science behind computers, but we also want to be able to take that knowledge and code it up. So how the hell are we going to do that? When in my explanation of this, I said, draw the nodes lower visually. How the hell do you do that in your code? How do you say, hey code, make this lower visually? So we're going to need a new way to track that same idea, that same concept of exploring an edge is going to advance you to the next level or the next distance number. So let's just track those levels or the distances from the starting node to any other node in the graph in a data structure. Which sure looks like a map to me. But we're actually going to use 3 different data structures to run breadth first search. So, and with graphs, I should have prefaced this earlier, but with graphs, we're not really learning a brand new data structure, strictly speaking, but we're combining the data structures we know about. Our graph is represented with an adjacency list, which is a hash map of values to an array list of values. So we took hash map, our key value store, we took array list, one of our sequential data structures, we mashed them together and we called it a graph. With breadth first search, we need to use some data structures to get this to work, to be able to get breadth first search working, but it's a combination of 3 data structures that we already know how to use. So let's talk about what those data structures are. I'm going to represent them visually here, but your task in the homework in task 8 is to code this up, actually create these data structures, maintain these data structures, and go through them. You'll, of course, also use the adjacency list throughout the execution of the program, but these are the 3 extra data structures you'll need to run breadth first search. All right, so first data structure is a queue. You're welcome to use the queue that we built in class or Java's built-in queue. I don't care what you use, as long as you know how to use whatever you're using. Like, don't go and grab Java's built-in queue if you don't know how to use it. I've seen students do that in the past. Like, actually read the documentation and whatnot. If you don't feel like doing that, just use the queue we built in class. Like, I built a queue for you. But regardless, you'll need some first in, first out data structure here. And this is going to track the nodes that we're going to visit the neighbors of. So this queue, where this is the front of the queue, this is the back of the queue, this is going to keep track of the nodes that we still have to explore the neighbors of. We're going to initialize this to just the starting node. So when we're setting everything up, we're going to say queue dot in queue the starting node. The starting node is the first node that we want to explore the neighbors of, so we're going to queue it up. Or in-queue it. Then we'll need another data structure. I'm using colors in the slides to represent the nodes that have been visited, but we'll need some data structure in our code to track which nodes have already been explored. And this is a data structure that we're going to constantly ask, hey, has this node been explored? Because if it's been explored, I don't want to explore it again. If it has not been explored, then I want to mark it as explored and explore it. So we need to have another data structure, which is going to represent these colors, which nodes are highlighted in orange. My favorite data structure for this is a set, but we've never talked about set all semester. I haven't showed you a set in Java at all. If you want to learn how a set works, I encourage you to do that. It's a fun data structure. It works exactly how you would expect if you've taken 191 or are taking 191. It's a data structure that does not allow duplicates. So if you add something to a set multiple times, you only get it in there one time. And it's very efficient to ask a set if a value exists in the set. Very efficient. I believe Java's implementation is O of 1. I believe sets work off of hash sets, but I'm not 100% sure on that. But it is efficient. More realistically, I would expect that most of you will use an array list for this, and that's perfectly fine. It's much, much, much slower, to the point where so many students were timing out in Autolab that I had to nerf my tests a little bit. You'll notice there's an easy and a medium test in Autolab and no hard tests. It's because I had to remove that one because too many people were timing out. But 116 isn't about efficiency, so it's fair for me to just remove that test. So if you want to use an array list for this, and whenever you explore a node, just add it to your array list. And then every time you need to check if a node has been explored, go through your entire array list in O of n time and find out if that node exists. Or use your array list.contains, which is going to be an O of n operation. It's going to do the same thing. It has to go through the whole array list. Which, when you have thousands of movies, does end up getting pretty slow. Slow enough to time out in Autolab. It must be tens of thousands of movies. Thousands one timeout. And we're going to initialize this by adding our start node. So we're marking our starting node as explored by adding it to whatever data structure we're using to mark our explored nodes. Some students also will use, which is a very efficient way to do it, a hash map of nodes to Booleans, initialize them all to false except the starting node to true, and then look up in O of 1 time in your hash map to see if a node has been explored or not. With O of n set up, but O of 1 lookups, it is very efficient. All right. That O of, for what it's worth, that O of n would be, I don't think amortized is even the right word there, but it doesn't matter regardless because it's being handled outside of an O of n loop. All right, and then our third data structure that we'll need to set up. So when you're writing your BFS code to find the distances, you want to set up all three of these data structures, initialize them, populate the starting node in each of them, and then run your algorithm. So the third data structure is going to be a hash map, or any key value store really, but hash map is the one we've been using. And I say map here because why'd I even open my mouth? I don't feel like explaining this, but I will now that I started. Map is the interface that hash map extends or implements. So map, now that we know about polymorphism, is the interface that that all maps need to implement. Hash map being one of the maps that the one that we've been using all semester, but anything that implements the map interface would be fine. Just like on the last slide, anything that implements the list interface, I'm not saying array list here anymore. Anything that implements the list interface is fine. Anything that implements the set interface, whether it be a hash set or any other set that you want to use, tree set, anything that implements the set interface is fine. Anything that implements the math interface is fine. We've just always been using hash map. So this is going to be a map that maps each node to its distance from the starting node. Now, I visually on the slide, I'm initializing each node to infinity because that is their actual distance. If the distance is not known yet, it's effectively infinite. And then if that node is never explored, it's not in the connected component and the distance is infinite. In your code, you'd probably want to initialize these all to -1, since that's what we're using to indicate a degree of separation of infinity. We're going to return -1 from our method. So you might want to initialize all those to -1 instead of infinity. And then initialize in that hash map the starting node to be a distance of 0. Or alternatively, just don't put them in the hash map at all. Just have a hash map of size 1 with just the starting node. That also works. And then if the other node that the other actor is not in this hash map at the end of the run of the algorithm, then you know they're not connected. And you can return -1. All right. So initialize the starting node. Its distance to itself is 0. So this hash map is storing each node's known distance from the starting node. So starting node to the starting node is 0, so initialize that one to 0. And this is where I would start thinking maybe this could be considered dynamic programming, because we're going through the algorithm and keeping track of some extra information. I forget the pure definition of dynamic programming, but this could be considered dynamic programming. All right. So now that we have our 3 data structures set up, we're ready to go through our algorithm. Oh, I gotta adjust here. We're ready to go through our algorithm. So our algorithm, I'm too low. Our algorithm is going to be DQ from the queue, explore the neighbors of that node, any neighbors that have not been explored yet, mark them as explored, in-queue them, and then update their distance to be the distance of the node that discovered them plus 1. Do that until the queue is empty. And that's the whole algorithm in a nutshell. I'm going to run through the whole thing, of course, but that's the algorithm in a nutshell. So we want to go to our queue. We're going to, while the queue is not empty, not to just completely give it away, but I told you I'd give heavy-handed hints here. But while the queue is not empty, which you should be visualizing a loop there, DQ. So we're going to DQ Carnegie. And when we DQ Carnegie, we're going to go to our adjacency list. you're going to get your adjacency list from your graph, say, give me all the neighbors of Carnegie. And it's going to say, oh, whoa, okay, I'll give them to you. So you get the neighbors of Carnegie, which is Case and Harvard. For each one of those, you're going to say, Case, ask this data structure, Case, have you been explored yet? And it's going to say, that data structure is going to say, nope, I've never seen Case before. And you're going to say, well, you have now. So you're going to add Case. Since it hasn't been explored, you're going to add Case to your explored data structure. You're going to enqueue Case. And then you're going to go to your hash map of distances and say, Case's distance is the distance of the node that discovered it plus 1. So we want the distance. Each one of these distances is the distance from Carnegie to that node. So if we can get from a node that can get from Carnegie to Carnegie with distance 0, and then we took one more edge to get to this node, we want to add 1 to this distance and say that's how long it takes to get to Case. It's going to take 1 edge. And breadth first search will guarantee that when you do explore a node, you will have explored it via a shortest path. It's one of the guarantees breadth first search gives us. So we found a shortest path from Carnegie to Case. The neighbors of the starting node, it's pretty obvious. Okay, they're connected to the starting node. They're going to have distance 1. But when we get to the end, it's less intuitive, and the algorithm keeps track of all that for us. Same with Harvard. So Harvard has not been explored, so we mark it explored, enqueue it, and mark its distance as the distance of the node that discovered it, plus 1. And we're going to dequeue Case. Case is going to check its neighbors. It's going to check Carnegie. It's going to ask this data structure, hey, I got a neighbor, it's Carnegie. Has it been explored yet? Data structure is going to be like, yeah, I've already seen Carnegie. Case is going to say, okay, yeah, I'm not going to do anything with that. So Case doesn't do anything with Carnegie. It checks if it's explored. The answer was yes. That's it. Don't do anything else. So you're picturing a while loop. That while loop is going to have another while loop. Or not a while loop, a for loop. I'm just giving away the code at this point. That's too much. That's enough that if 2 students talked at that much detail, that's a quick way to get an AI meeting. So let me stop with that detail. So Case is going to ask if Carnegie's been explored. It has, so it's going to shut things down. It's going to its other neighbor, Lincoln. It's going to say, hey, has this been explored? The answer is no, so it's going to explore it, mark it as explored in this data structure, enqueue it in this data structure, and go to this data structure and say Lincoln's distance is whatever Case's distance is plus 1. Because we can get from Carnegie to Case with distance 1, and it took us 1 more edge to get to Lincoln, so bump it up by 1. Lincoln's distance is 2. Very similar thing to Harvard. Harvard is going to check Carnegie. It's been explored. It's going to check BBN, so do nothing. It's going to check BBN. It has not been explored, so mark it as explored, enqueue it, and set its distance equal to Harvard's distance plus 1. And now, in our last run of breadth first search, I said Lincoln and BBN are going to fight over MIT, and I'm just arbitrarily going to choose Lincoln to be the one that wins and the one that discovers MIT. In our code, we don't actually code anything that says how to break ties or anything. The ties are just broken implicitly by the order in which the nodes are visited, and that's going to depend on the order of the nodes in the adjacency lists, which will depend ultimately on the order in which the nodes have been added, or the edges have been added to that adjacency list. So when we explored Carnegie, we just said, well, the adjacency list is going to be Case then Harvard. That's what that array list in the adjacency list is going to be, and that is how this tie was broken. Because Carnegie, we enqueued Case before Harvard, which means we enqueued Lincoln before BBN, which means Lincoln is going to be dequeued before BBN, and Lincoln is going to find MIT. Lincoln's going to check Case, say this has already been explored. It's going to check MIT, say this has not been explored, mark it as explored, enqueue it, set its distance equal to Lincoln's distance plus 1. Now when we dequeue BBN, BBN is going to check Harvard, it's been explored. It's going to check MIT, it's been explored, so it just skips it. and check rand, explore rand, and Q rand, set rand's distance equal to BBN's distance plus 1. And we keep repeating the process until the queue is empty. So we're going to repeat the process. MIT, DQ, check Lincoln, it's been explored, do nothing. BBN, do nothing. Utah is a new node, mark it as explored, and queue it, set its distance equal to MIT's distance plus 1. We can get from Carnegie to MIT through 3 edges, and it took us 1 more edge to get to Utah. So Utah's is MIT's 3 plus an extra 1 edge. And breadth first search guarantees that that will be the actual distance. For example, if Utah did have a shorter distance, if Utah had distance 3, the algorithm would have found Utah before MIT was ever DQ'd. So the queue is what's keeping track of the order to make sure that when we discover a node, we actually did discover it via a shortest path. Because the starting node gets enqueued first, then its neighbors get enqueued, all the nodes of distance 1 get enqueued, then all the nodes of distance 2 get enqueued, then all the nodes of distance 3 get enqueued, etc., etc. And the queue will always maintain that order because we're using a first in, first out data structure. If we changed our queue to a stack, guess what we get? It's depth first search. That's the difference between using a queue and a stack here. That's the difference between depth first search and breadth first search. All right, so let's keep going. Rand, by the way, depth first search isn't a 116 topic. We're not going to discuss it. We're not going to talk about it. But it's a similar thing. I'll do it very briefly. It's a similar thing, except you explore a neighbor, then explore one of its neighbors, then explore one of its neighbors, one of its neighbors, one of its neighbors, etc. And you keep going in a depth first fashion. You go deep into the graph, and then you backtrack and explore anything that hasn't been explored on the way back. So Carnegie, this edge between Carnegie and Harvard, likely wouldn't be explored if we went to Case first. Actually, it wouldn't be explored. Because one way or another, we're going to get to Harvard. But depth first search just doesn't give us really much useful information. Whereas we can get the distance information from breadth first search. We can't get the same information from depth first search, which is why we use breadth first search instead of depth first. All right, but let's keep going. Rand, it's going to check BBN. It's already been explored, so don't do anything. But then it's going to explore 3 other nodes. It's going to mark them all as explored and queue them all and set all their distance equal to Rand's distance plus 1. So they all get distance 4. So we see all of our distance 4 nodes are in the queue, and 0 of our distance 5 nodes are in the queue. The queue is going to maintain this order to make sure that the nodes are always enqueued in order of distance. So Utah, SDC, 2 of its neighbors have already been explored, do nothing, but it finds SRI. Mark SRI is explored, enqueue it, set its distance to 5. UCLA is going to find Stanford, enqueue it, mark it as explored, enqueue it, says distance equal to 5. And then we still have nodes in the queue. Everything's been explored. Like, we know everything's done at this point, but our algorithm is going to run till that queue is empty. So we are going to run through our code. I suppose you don't have to code it up like this. You could say once you find the end node, just return its distance. But we're going to run until the queue is empty. So UCSB is going to check all of its neighbors, see that they're all explored, and effectively do nothing. SDC is going to check all of its neighbors, see that they're all explored, and effectively do nothing. SRI, same thing. All of its neighbors are explored, so do nothing. Stanford, all of its neighbors are explored, so do nothing. And now we have the entire connected component of the starting node has been explored. And we have all of the distances from the starting node, Carnegie, to any other node in the graph. So from Carnegie to Stanford, the distance is 5. Carnegie to SRI, the distance is 5. UCSB, the distance is 4. 1, 2, 3, 4. We follow the yellow lines to get the actual path. And we have all those shortest paths uh, between the starting node and any other node, and the distances. More importantly, the distance. We actually don't have the paths yet. That's the next thing. But we have the distances. So this is what you need to code for your homework. That's task 8. Building that graph, running breadth first search with these 3 data structures, tracking the distance numbers, and you're asked to find the distance or degrees of separation between 2 nodes. So you would pick one of those 2 nodes to be your starting node. You would run the algorithm. That gives you the distance from the starting node to all other nodes in the graph. And then look up in this hash map, say, okay, where's my ending node? Say I was asked to find the distance between Carnegie and Rand. I would start at Carnegie or Rand, either one. But I would start at Carnegie, run the whole algorithm, get my data for every node, and then look up, okay, so what's the distance from Carnegie to Rand? 3? That's what I'm returning. That's my degrees of separation. That's my distance between those 2 nodes. If the ending node has never been explored, I'm returning -1. That's task 8. I'm on my phone. I don't know where to look for the time. 12:20. I'll pause here for questions, because the next thing is pathfinding. Pathfinding is something you're not asked to do in 116, at least not this semester. It was one of the kind of bonus homeworks, or extra torture homeworks as the students treated them. You're not asked to do it. I think it's still super interesting, and I'm still excited to show it to you. But it's not something that you'll have to code this semester. So I want to take a breather here and wait for any questions, because if you understand everything that you just saw, you're in good shape to tackle task 8 and get that one done. If you don't understand everything that just happened, I want your questions. Give me your questions. We have one more run. The next run of breadth first search is actually going to go pretty quick when we do the pathfinding. And then we have a memory diagram to go. Then we'll be done with content in 116. That's scary how fast it goes. In 6 weeks. Well, 5 weeks of content. I can't really add new content next week because I won't have time to assess you on it. Especially when the grading is pass-fail, you have to complete everything. I can't cover new content next week and give you 2 days to study it. All right, we go to, I don't know why I always forget. We go to 1:30. I usually have my phone right here and I got my alarm set, but we go to 1:30, so we got 68 minutes. We got plenty of time. And I feel like that's been long enough. I'm assuming there's no questions, so let's keep rolling forward. All right, so we get the distance of each node, but what if you want to do pathfinding? So what if you actually want the path between each node? So you're writing some code. Say you're writing a game where you're coding the AI that's going to work in a grid-based top-down view game, and you want the AI to be able to find the shortest path to the player and hunt down the player, which was a homework assignment. Actually, that was the bonus assignment, wasn't it? Which was a homework assignment I used to run, which I think I'll bring that back someday. In one of the tasks, not a bonus assignment. But anyway, so what if we want to find the actual path between 2 nodes? So instead of tracking the distance, we're just going to make one pretty small change to our data structure here. Instead of tracking the distance like this, we're going to track the node that explored that node. So instead of taking the node that explored that node's distance and adding 1 to it, instead we're going to remember the node itself. We're going to keep track of which node explored each node. So Carnegie, we're going to have some special marker to say that, like null maybe, to say that Carnegie is the starting node. So nothing discovered it, it's the starting node. And then each time we explore a node, we're going to remember which node explored it. So Harvard and Case were both explored by Carnegie. BBN was explored by Harvard. Rand was explored by BBN. MIT was explored by Lincoln. And you get the idea. We run through the whole algorithm and keep track of this information. Which node discovered each other node in the graph, with the starting node being marked with some special indicator. So if we keep track of this information and we want the path, say we're asked to find the path, a shortest path from Carnegie to Stanford, we choose Carnegie as the start node, or Stanford. We could start with Stanford either, but we already have it set up for Carnegie. Start at Carnegie as the start node, run the algorithm, keep track of this information, and then when we want the path, we're going to start at the end node and work our way backwards while building this path until we find this start indicator. So we're going to start at Stanford, and we're going to say, okay, Stanford, who discovered you? It's going to say UCLA. So we know UCLA is the second to last node in the path. The last node is always going to be our ending node. Second to last one is whatever discovered the ending node. And then we just repeat the process. UCLA, who discovered you? UCLA, oh, I already have it highlighted. UCLA, who discovered you? Well, Rand discovered me. Okay, Rand, who discovered you? Well, BBN discovered me. BBN, who discovered you? Well, Harvard discovered me. Harvard, who discovered you? Carnegie discovered me. Carnegie, who discovered you? Yo, I'm the start node. No one discovered me. I discovered myself. And then once we find that start node symbol, we have our path. We have a shortest path from Carnegie to Stanford, which happens to be the shortest path in this case. Yeah, this is the shortest path. So we have the shortest path from the start node to the end node. So that's how we can do path finding, which, cool, like this helps us route packets through the internet, I guess. But what about the game example I mentioned? Well, say we have this game board where we have a 2D top-down view. We have a player character moving around, and these blue circles are going to be the AI characters that we want to code. And the AI, we want them to hunt down the player and shoot these little projectiles at the player, but while avoiding walls. This level is designed in a way that if the AI is doing something dumb, like just going directly towards the player, it's going to get caught right here, and it's not going to move anywhere from there. So we want our AI to be smart enough to avoid walls. And that's where things get a little trickier, where we have to use some code, something like BFS. So when we're playing the game, we're going to see this. We're going to move around this map. We're going to shoot things, and we're going to be hunted down by these AI that are trying to shoot us. But when the AI is playing this game, they're just going to see this graph. They're going to take this game board, or running the code that students used to have to write for this assignment. They would take this game board and create this graph from the game board where each node is a tile in this grid, and there's a edge between two tiles if they're adjacent in a cardinal direction, left, right, up, down, and the other node is not a wall. So the walls, we actually just don't create nodes for them, so there's no edges, so the AI knows that it can't go there. And then when, say, this AI wants to hunt down the player, it's not going to go directly to the player. It's going to run breadth first search with its location as the starting point, run breadth first search, and find the shortest path in this graph to the player. My eyes always bug out here. Right here the player is. Well, arguably right here. It's right here. So it's going to find this shortest path to get to the player and then traverse that path to attack the player. And then as the player is moving around, it would keep running breadth first search to get the updated shortest path. So if the player is sneaking up around here and then goes to the other side of this wall, at some point the AI is going to detect that there's a shorter path to go up this way, start hunting the player that way. So this is a way that we can use breadth first search and this shortest path, the path tracking and all that, to be able to get AI that's smart enough to avoid walls and hunt down a player as we're running this game. So we can have smarter AI than just like subtracting the vectors and traveling in this direction. Um, we don't want to do that. We don't want AI that's just going to get caught on walls and be really dumb. Just get jammed in this corner and start shooting into the wall. It'd be easy to code an AI like that, but that AI is really dumb and it makes your game really boring. If you have really dumb AI, it makes a game not so fun to play. But great. We have degrees of separation between actors, so let's talk about how to do this. I talked about it briefly earlier in the lecture, but I promised I'd have a few slides and revisit it, so let's do that now. How does this apply to degrees of separation between actors? We want to play our degrees of separation game, and we have data that looks like this. We have the title of a movie, and then the list of actors, which you already wrote the code to parse. Well, I know a lot of you haven't, but we already had these introduced the assignment that parses this code, parses this data, and gets this in a movie object with title and an array list of actors. So we want to take that array list of actors and build a graph out of it. So we want to build a graph where any actors who are in a movie together have an edge between each other. So we have an edge or a node, Jennifer Lawrence, with an edge between to another node, Josh Hutcherson. Wow, I've never said that out loud. Hutcherson, and Jennifer Lawrence to Elizabeth Banks, and Josh Hutcherson to Elizabeth Banks. So we'd have a node graph with 3 nodes that are all connected in a triangle. Then when we add the Lego movie, we're processing this. We're going to add Chris Pratt as a node, Will Ferrell as a node, Elizabeth Banks as not a new node. Those 3 actors will all be connected by a triangle, but Elizabeth Banks will be that like connection between the 2 triangles. I don't know why I tried explaining it like this. But any actor that exists in your data set is going to have a node, and they're going to have an edge connecting them to each other actor that they've been in a movie with. So we build that graph and run breadth first search. So if 2 people are in a movie together, sure sounds like an edge to me. So going through this list and creating all your edges for each movie. And then the shortest path between 2 people is exactly their degrees of separation. The length of the shortest path, or the distance between 2 people, is exactly their degrees of separation. So I can go Jennifer Lawrence to Elizabeth Banks to Will Ferrell. So Jennifer Lawrence to Will Ferrell is going to be degrees of separation 2. Zoe Saldana to Josh Hutcherson, Zoe Saldana to Chris Pratt to Elizabeth Banks to Josh Hutcherson, degrees of separation of 3. In this data, of course, their actual degrees of separation is much smaller, I'm sure. But in this, for this data, if these are the only 3 movies in existence, or these are the only 3 movies in your test file, or if these are the only 3 movies in one of my test files, which they are in one of my test files in Autolab, then that would be their degrees of separation. Everything you need for task 8, which I feel like I really walk you through task 8. Yeah, students inevitably have a lot of trouble with task 8. So if there's anything you don't understand about that, if you're not ready to write that code right now, now's the time to let me know. With only 21 people watching, most of the class isn't even watching it, at least not live, so can't really ask me questions, but they're going to be the ones that'll have all the questions. It's a fact of life that I have to deal with. All right. So if there are no questions, let's get on with a memory diagram. We still have tons of time. I feel like I'm just flying through. Well, usually I do get more questions. This slow me down a bit. But if y'all don't have questions, I guess I'll just keep going. And it's a memory diagram. So this is the code we want to work with. Let's just go right to the memory diagram. Let's just do it. So always start with the main method. Excuse me. We're going to get to the graph constructor. The graph class has a constructor which initializes its question, yes, initializes its adjacency list to a new hash map, sets everything up. That's all old hat. I don't think I have to explain that. I guess my only question for task 8 is, if there's a graph for each movie, how would we code it to make sure we aren't increasing the distance when going between actors in the same movie? So there's only one graph for all movies. So this, like in this data, you would have one single graph. Each actor is going to have its own node, but you're going to add an edge for each actor, and each. Let me back up. You're going to add an edge for each pair of actors in a movie. So when I'm processing this, I create one single graph before I start processing the file. And then when I go through this movie, I'm going to go through each pair of actors. So I want to say add an edge for Jennifer Lawrence and Josh Hutcherson. Add an edge for Jennifer Lawrence and Elizabeth Banks. Add an edge for Josh Hutcherson and Elizabeth Banks. I'm adding those 3 edges to my single graph. That graph, the add edge method, is going to add the nodes if it's the first time I've seen that node. But when we get to the second movie, Chris Pratt and Will Ferrell, adding those to the graph, and then Chris Pratt to Elizabeth Banks, the graph code is going to say, well, I've already added a node for Elizabeth Banks, so I'm not creating a new node. I'm just going to add the node Chris Pratt and then add an edge between Chris Pratt and the existing Elizabeth Banks node. So just one single graph, not a graph for each movie. So each node in the graph could be a hash with all the actors in it, maybe. Yes. If I'm understanding you right. The code might help us see that one. So we're going to have one hash map. Oh, yeah, I think that is what you meant. We're going to have one hash map, and like n for the homework is going to be string. And like one of your keys in your hash map is going to be Elizabeth Banks. And then Elizabeth Banks' array list is going to have, I forgot the actors now, Jennifer Lawrence, Josh Hutcherson, and Chris Pratt, and the whatever the third actor was. Oh, I forgot the third actor in the other one. So Elizabeth Banks' adjacency list is going to have all those actors from all of the movies that Elizabeth Banks is in. It'll have all the actors from all the other actors from any movie that she has been in. Because they're all neighbors of her, because she's been in movies with them. And when you add an edge, the only method you're calling is add edge. Add node is private, in fact. So you're only calling the add edge method. You add an edge, then it's going to call add node and initialize that array list if it's the first time that you've added an edge for that particular actor. But if you're on like the second movie that actor's been in, add node isn't going to do anything because the adjacency list already has been initialized, and it's just going to add to that adjacency list. And of course you want to use add bidirectional edge so you get both directions of the adjacency list. For this memory diagram, we're going to use airports and connecting flights, and we're going to say that connecting flights are one way, that they're not going to have a return flight that's taking passengers. Just to get the add edge method in here instead of add bidirectional edge. And I'm going to remember to move my face this time. Like hanging out right here in the code, because I know there's no content that's going to appear right there. All right. So when we call the graph constructor, it's going to initialize the hash map. Remember, we use these T-charts for hash maps and array lists. This is going to be keys and the values that they map to. And I'm picking random numbers, 350, 200. We're used to that by this point in this semester. And one instance variable, this is declared outside of any of the methods, so it's an instance variable. And then new resolves to a reference to the object that was created, and that's stored in the graph variable. All that better be old news. If you have any questions about that, I'll still take them. I'll still be happy to explain it. But yeah, we've been doing that since week 2. Like I said, it isn't even that long ago, but still. All right, and then we're going to call add edge. with Buffalo and Washington D.C. as the airports. So graph.addEdge, graph.addEdge. So we're calling it from an object of type graph. We look in the graph class for an addEdge method. There's only one class in this example, so that's not super interesting. But just a reminder how our polymorphism works, because you do have the polymorphism quiz on Tuesday as well. And then this is a reference to the calling object. So we get addEdge. This is a reference of the calling object. From and to are buff and WDC. This is a graph of strings, so we're going to give it 2 strings. So effectively n is going to be string in all of our code here because our graph is of string. So we create a graph of string, n is going to be string. So we give it 2 strings, addEdge, from and to. The first thing addEdge does is this.addNode. This.addNode, we're calling it from an object of type graph, and this is going to be 350, the calling object. AddNode, we got from, which is buff. So A is buff. Why is there a variable called A? And then we're going to check if this dot adjacency list dot contains key of A. If this dot adjacency list dot contains A, and the memory diagram already updated, but it wouldn't contain A. It doesn't contain buff, so we're going to this dot adjacency list dot put. So at this hash map, we're going to put A, which is buff, as the key, and new array list as the value. We're creating a brand new array list, so get that on the heap. And then buff maps to that new array list that we just created. Same thing with our 2, Washington, D.C. We're going to call addNode. It is not found in the hash map, so we're going to create a new array list and initialize it. We're seeing our lazy initialization in action here, where Washington, D.C. is now mapped to this 120, this empty array list. And we get to do the action here, actually adding the edge. So we're initializing these 2 nodes because we've never seen them before. And then we're going to safely be able to add the edge. So this dot adjacency list dot get, here we've seen this before, but this is where things get a little bit tricky. Get from, so from has to be, this expression has to be evaluated. So we start back at the stack frame again. From is buff. And then get, we were calling that method from this hash map. So get buff, which is going to resolve to this reference, OX480. And then dot, so we're going to follow this reference, dot add. So we're calling the add method from this object, this array list. And we're adding 2, so we go back to the stack frame to resolve this expression, to WDC, and adding WDC to this array list. So we effectively added an edge from Buffalo to Washington, D.C. by following all those references and getting it in the appropriate array list. Now, if we were adding bidirectional edges, we'd have another line that's this dot adjacency list dot get to dot add from, and then we'd add Buffalo to this adjacency list. But we're saying that these are not bidirectional edges, these are one directional edges, so we're only adding one edge in this example. Okay, let's do it again. Add edge, Washington, D.C. to JFK. When we call add edge, we're adding each node first. Washington, D.C., we're going to check our conditional, this dot adjacency list, this dot adjacency list dot contains WDC. It does contain WDC. So that resolves to true, but this is a not. So if not true, this is false. We skip over this and we don't reinitialize it, which is important because if there are edges in the adjacency list already, we don't want to overwrite them with a new array list. We don't want to do that. So we're going to skip that, and the method does nothing. When we get to JFK, we have not seen JFK yet. So we're going to add JFK with a new array list. So we got another new array list and a reference to that array list in our hash map that represents our adjacency list. And then we can actually add this edge too. Oh, that should be grayed out. That's crossed out. So this dot adjacency list dot get from, which is Washington D.C., resolves to OX120 dot add the 2, and our 2 is JFK. So we add JFK to this array list. And repeat the same thing for Toronto to Buffalo. So Toronto, we haven't seen that before, so add node is going to add that node with a new adjacency list. Buffalo has already been seen before, so we don't want to erase this information. We don't want to lose this edge, so we're not reinitializing that. And then we're going to add Toronto to Buffalo. We're going to add that edge in our array list. So that set up our entire graph. We got our graph looking the way we want it to look. It has all the information of these 3 edges in there. And notice we do have one adjacency, one array list that is empty. There's no outgoing flights from JFK in this example anyway. Obviously there are in real life. But in this example we don't have any. So we do have an empty adjacency list, an empty array list, and that's perfectly fine. But we do want that adjacency list to exist, or else we're likely to get in a key not found error when we're trying to look up JFK in our adjacency list. So it's important that that is initialized. All right, and then we're going to create a path. We don't put our array list constructor on the stack or anything, so it just kind of appears. None of these array lists or the hash map constructors we put on the stack in our memory diagrams. So path 1 gets a reference. I made up 196 for this one, and it's going to have the values Buffalo, Washington, D.C., JFK. And we want to check if this is a valid path in the graph with this valid path method. So we're going to call valid path graph.validPath. So the calling object is of type graph and has reference OX350. So this is OX350. Path 1 is the argument. Path 1 parameter path gets that value, which is the reference OX196. And then we're going to start a loop. So we have our dashed box for our code block. The looping variable, the initialization variable, is declared within the code block. So I is declared within the code block, gets an initial value 0. We check the conditional if I less than path.size minus 1, which is true at this point. Path, where's my path? Path.size, it has 3 elements. Minus 1 is 2, so 0 less than 2 is true. So we're going to execute the loop. And notice that this is, I don't think I have a slide on it. So notice that this loop is set up. This is something we've done. I don't know if I did this explicitly in lecture, but it's something you've definitely done before. But I still want to point it out because it's still, it's kind of a tricky thing in programming. But I have a loop where what I want to do in this loop is go through this path and check if each consecutive pair of nodes are connected by an edge to make sure that check if this is a valid path in the graph. So when I'm going through this loop, I don't want to loop through every single node in the path. What I want to do is loop through every adjacent pair of nodes in the path. So I don't want to loop through Buffalo, WDC, JFK. I want to loop through and check Buffalo and WDC to check if they have an edge connecting them. Then I want WDC and JFK check if they have an edge between them. And then I want the loop to stop. So I'm actually only iterating twice in this loop. That's what I want. That's the behavior I want. So normally we would loop through everything, and if we're using indices like this, we would say I less than path.size, and that's going to give us 0, 1, and 2, and then when I is 3, the condition's going to be false, and the loop's going to break. Or we would do I less than or equal to path.size minus 1, and that's going to give us the same thing, 0, 1, and 2. But I don't want that. I want to only iterate twice. So I'm going to use less than instead of less than or equal and the -1. And this is going to stop me one short of the last index. So I'm only going to get 0 and 1 as the values for I. And once I is 2, this condition is false and this is going to break. So I'm never executing the loop with I as 2, which is very important that I'm stopping one index short of the end because I'm going to get a value at I plus 1. So if I is ever 2, I plus 1 is going to be 3, and I'll get an index out of bounds error right here. So I have to be careful with the way I set this up to make sure I'm checking every adjacent pair of nodes and also not asking for a node that doesn't exist, that goes off the edge of the array list. So with less than and -1, I'm stopping short of the last node, and then in my code, I'm advancing to the next node and advancing up there. So I got my loop set up in a little bit different way, where if you're iterating over all the values, I would just say for string airport in path and just use an enhanced for loop. But since I need to do something kind of tricky, I do have to remember how these regular for loops work and manipulate that to get exactly what I want. All right, and then I'm going to call rConnected. So this dot rConnected. So from this this graph, path dot get of I, path dot get of I is 0, so buffalo, and path dot get of I plus 1, which is WDC. So I'm calling rConnected with Buffalo and Washington, D.C. And then I have this big old Boolean expression here. So this rConnected is going to say this dot adjacency list dot contains key from. So does it contain the key Buffalo? It does. So I want to make sure that the starting node exists. This is where I'm still seeing all kinds of Piazza questions and stuff of like null pointer exceptions, index out of bounds, key doesn't exist. When you get those runtime errors, you usually want to have a check like this. Check if the thing you're about to access exists. This is true, like this is general programming advice. If you're going to go to a hash map and try to get a value at a specific key, you should have in your code some assurance that that key exists or some backup plan if that key doesn't exist in the hash map. Same with indices in an array list, and the nulls. Like, y'all, like, check for null. If you're handling a node-based data structure, check for null, like, everywhere. I see so many people in there testing the linked list that's returned from your get song list from your playlist. So many people just assuming that the list is exactly what you expect it to be. But you're writing a test. You shouldn't make assumptions in your test. Always check for null. Gotta check for null. So make sure it contains the key before you get that key, get the value at that key. So if it contains the key, it does. Then we go to it again. From rConnected. This dot adjacency list dot get from, which is Buffalo. So get the value at the key Buffalo. That's 480 dot. So follow the reference. Contains 2, which is WDC, and it does. It's right here. So that's going to return true. They are, Buffalo and WDC are connected in that order. This is checking a directional edge. We're not concerned with WDC contains Buffalo. We just want to know if Buffalo contains WDC. Can I get from Buffalo, hop on a flight, and go to Washington, D.C.? All right. So that returned true, and we have a not here. So that'd be false. So if false, we're skipping this block, and we go back up to the loop. I advances to 1. We got I plus plus, so I increments to 1. And then we're going to do the same thing. If this dot rConnected of path dot get I, which is 1, WDC, path dot get I plus 1, which is 2, JFK. So we get Washington, D.C. and JFK. This is the calling object. And we're going to do the same thing. If this dot adjacency list dot contains key, this dot adjacency list dot contains key WDC, that's true. So we're going to move on to the and. Oh, I'm using a shortcut evaluation here. I didn't explain this, did I? There's a lot going on in this line. This is the part of the semester where I assume people want more like tips and tricks. So I did something kind of fancy here. So this takes advantage. I mentioned the whole. Yeah, I didn't finish my thought there. So this takes advantage of something called shortcut evaluation. So an and, this is a logical and of these two values, which means this will only resolve to true. This Boolean expression is only resolving to true if both values, if both left-hand side and right-hand side of the logical and are both true. It's basic logic. If either one of these is false, it's false. If they're both false, it's false. The only way that truth table is going to spit out true is if they're both true. If the first argument of a logical and is false, there's no possible way that we can evaluate to false. It doesn't matter what the second thing is, what the second operand is. Does not matter. We're always resolving to false if the first thing is false. So what Java does, and what a lot of languages do, is it'll check the first operand. It'll completely evaluate this expression, which should be a Boolean expression. It'll completely evaluate this. And if this one resolves to false, it resolves the and to false without resolving the second operand. It will shortcut the evaluation and not evaluate the second operand. So that's how I'm getting away with this. I'm saying if this contains key, I read this as if the adjacency list contains this key, then do this. I kind of read it as an if statement, just by using this a lot, seeing it a lot. Because of the shortcut evaluation. If this is false, this code never gets executed. If this is true, then this code will be executed. So this is what gives us the protection. This will never be executed if the adjacency list doesn't contain that key. So I'm not getting a key doesn't exist error here, or exception, because if this is false, this doesn't get ran. So that's like a more advanced, categorize that in tips and tricks. You don't need that for 116, but if you made it this far and you're still coming to lecture and paying attention, I assume you want to see some of that stuff at this point. So it's a nice trick. You'll see this throughout your programming career. Shortcut evaluations. The same is true if this is an or and the first operand evaluates to true. The second one won't be evaluated because it's always going to evaluate to true. The whole expression is going to evaluate to true. There's no reason to run the second one. One thing you have to be careful about is when you're calling methods in as the second operator of a Boolean as the second operand in a Boolean operator that has side effects. Sometimes you're not going to get those side effects because you'll get shortcutted and the second one won't be executed. The easy fix to that is don't call methods for their side effects if they're part of a Boolean expression, and just avoid that. But I have seen developers do that on purpose because they want the side effects in certain situations but not in others, and they use leverage shortcut evaluations to do that. So neat little thing, neat little programming thing that'll come up quite often, fairly often in your careers. I mean, I guess depends what teams you go to. You might go on a team where they discourage that and you won't see it. You might go on a team where they absolutely love it and embrace it. But I'd say you're likely to see it quite a bit. All right, so it contains the key. I think we checked if it contains the key, and then we're going to get adjacency list. This dot adjacency list dot get WDC dot contains JFK. It does. Oh yeah, because we're on the first path. And then technically I should have wrote it here. Technically I hits the value 2, but once it's 2, it's 2 less than 2, which is false because it's strictly less than. So we break out of the loop. And then another trick, this I think I've used earlier in the semester, but if I haven't, let's talk about it. And if I have, then we'll do extra review on it. So this is a common pattern where I'm taking advantage of return statements to get the value that I want returned from this method. So if ever I come across two adjacent nodes that are not connected by an edge, I'm immediately going to return false and just get on out of there. This is not a valid path, and just exit the method as soon as I can, as soon as I determine that it's not a good path, not a valid path. But if I make it through every pair of nodes and this is never executed, that's the only possible way that I can get to the end of the loop naturally without shortcutting with a return statement. So if I ever reach the end of this loop, I know that I checked every pair of edges, or every pair of nodes, and they all were connected by edges because I never got to this return false, so I can safely return true down here. At first glance, this method just looks like it always returns true. The last line is just return true. But since I have this return statement in the middle of the method, it can return false if that return statement ever gets hit. This, in certain communities, this is discouraged to use return statements as a way of control flow. Scala didn't like you doing this at all. When I taught this course in Scala, the Scala community, I should say, when I taught this course in Scala, I would never do this, just to embrace that community. In Java, I don't think they care so much that they're okay with this. So since I got to the end of the loop, I can safely return true and say this is a valid path. And print true to the screen for what it's worth. All right, and then let's create another path, JFK, Washington, D.C., Buffalo. And run through the same thing. So valid path of this next path, path 2. Loop is set up the same way. The path is the same length. So we're going to see I equals 0, then 1, and then technically 2, and we're going to break. We're never going to execute the loop with I equal to 2. We're going to call R connected JFK to Washington, D.C. So R connected, this dot adjacency list dot contains key JFK. It does. So we will execute the right-hand side of the AND operator. This dot adjacency list dot get JFK dot contains Washington, D.C. It does not. So that's going to return false. So this call results to false. We're going to negate that. So if true, we're going to execute the block, the code block for the if statement, and return false. We're never going to get I equals 1. We're never going to check the second edge because we found an edge that doesn't exist. We're immediately getting out of there. We're returning false and then printing false to the screen. And that's it. That's our really last bit of content that you're going to be assessed on. We made it. We made it to the end of the content. There's a lot more work to do, though. Not so much for me, but the office hours and stuff for sure. But a few more quizzes. Most of you have a lot of homeworks to do, a lot of programming tasks. But that's the end of content. That's the end of what you're responsible for in this course and what you're expected to learn from 116. That's fast. In 5 weeks, you'll learn everything you need to know, and then another week to wrap things up with assessments. Whew. But we do have an extra half hour. So what I want to do, I shouldn't say an extra half hour, but is go to IntelliJ. Well, first of all, if there are any questions, I'll take questions before I go to IntelliJ. Or rather, I'll take questions. I'll deviate from what I'm doing to take questions. But let's go to... I want this one. I think it's being called. And... and run the debugger. Let's get some good debugger experience in here. So I got a question on classes 2 quiz. I have a submission I can view, but my grade is 0 because no submission. Can I send an email about it? Yeah, absolutely. Yeah, if we missed your submission, by all means, send me an email. Let me know. Send an email to both Gerline and myself if you can, if you have her email. Because that's something we definitely have to fix. You can see your submission in Autolab too. Yeah, that's something we must have just messed up. I hope that's something we can get resolved for you pretty quickly. Alright, so let's run the debugger. Let's see this. I feel bad about that if we truly just missed that. I feel bad about that one. I definitely want to get that fixed for you. So here's our UCLA, Stanford, our early days of the internet example. I just want to run the debugger to show you how this is going to look in the code and just running, and more debugger practice in general. So reminder, the debugger is showing us everything that's happening in memory. So we have a main method on the stack. So we have the main stack frame, and then we're calling the example method just the way I have my code organized. And the example method, this stack frame is on the stack, and there's no local variables yet. But we're about to call the graph constructor. The graph constructor goes on the stack. So this is the stack. This is showing us every stack frame on the stack. And when we click on a stack frame, it's going to show us all of the variables in that stack frame. So these are your solid boxes in your memory diagram, and this is what's inside the solid box. So when we call the graph constructor, it has this, which is a reference to the graph that's being created. It even tells us that it's being initialized. The object is being initialized. And if I click on a reference to an object, this stores a reference to a graph, which is OX770 in this case. If I click on this arrow, it's going to take me to the heap and show me all of the instance variables associated with that object. I can see it has an instance variable named adjacency list, which is currently null. If you declare a variable that stores a reference but don't assign it anything, it does get the default value of null. It's not something I expect you to put on your memory diagrams, but something that might be useful later in your careers to know that this does get initialized to null. So like when you're creating your empty linked list, you're creating your empty root node for your trees, you can just declare it and not assign it to anything, and that's going to assign it to null. I usually like explicitly assigning null if I'm ever doing that. I just want to make my intentions as clear as I possibly can and eliminate any confusion. If somebody's reading my code and says, oh, did they mean for that to be initialized to null or not? If I put equals null, there's no question. They know that I meant to do that, that I'm doing that on purpose. But we're about to overwrite that anyway. We're going to go into the hash. Well, we're not going to go into the hash map constructor. The debugger is going to skip it. You can... I feel like I'm missing some buttons here. I might have to update IntelliJ or something. But there should be another button that says, I know you're going to skip the next thing, but go into it anyway. Because step into is going to skip the hash map constructor because the debugger agrees with us that going into Java internal code with the debugger is kind of pointless. So it's going to skip over that, give us that adjacency list, which is now a hash map at 771 or OX771 in our memory diagrams, which is an empty hash map. Then we'll call add bidirectional edge. That puts a new frame on the stack. Oh, and notice that the other frame is destroyed. Once a method call ends, that stack frame is actually destroyed. It's removed from memory. In our memory diagrams, we cross it out to indicate that. In my slides, I gray it out to indicate that. But it is actually removed from memory. It's completely deleted. It's gone. So now we put another stack frame for add by directional edge. It's executing on line 22 right now. By the way, this keeps track of where the execution is. This is at line 83. That's where it's waiting for a method to return so it can get control again. Add bidirectional edge is going to call add node on UCLA. This is still a reference to that graph, which has an empty adjacency list. A is UCLA. We're going to check if it contains UCLA. It does not, so this whole thing evaluates to true because we have a not false. So we're going to add UCLA to our adjacency list with an empty array list. So once we, and then sometimes the debugger gets weird sometimes. For some reason it does get into Java code in some cases. I don't exactly know why. But here, if you ever find yourself in a situation like this, like we're deep into hash map code at this point. If you ever get into something like this step out button is going to run your program until the current stack frame ends. So I want to go until this stack frame ends. That gets me back to the put stack frame. I'm going to go until that stack frame ends. And now I'm back to my add node stack frame. So even if those stack frames created more stack frames, it'll just run until all of that's done and the current stack frame ends. So now we got an adjacency list of size 1. Now I do get the arrow because there's actually something to see in there. UCLA to an array list. That key maps to an array list of size 0. And since that change happened on the heap, by reference, if I go back to my other stack frame, in example, I have a reference to the same exact graph on the heap, so I can see that change from this stack frame. This stack frame does see that same change because it has a reference to the same exact graph. 770, 770, it's the same graph. It's the same object on the heap. They're both looking at the same location in memory. Add node, we can watch that. We can, but just to show you more debugger buttons, we can see what add node does and go through that whole thing. It's the same exact thing that happened with add node of 1. It's going to add Stanford to the graph. Since I'm not too interested in seeing that again, I'm going to click the step over button, which will skip the next line. It'll execute the next line, but it won't show you any of the execution, including any stack frames that are created while that line runs. It's just going to skip over it, and then we can see that our adjacency list does have Stanford with an empty array list in it. So that line did what it was supposed to do, but it's not going to show us any of the nitty-gritty details if we say we don't want to. In fact, I'm going to skip over these lines too, just in case it wants to take me into Java code again. I'm going to skip this one, and we can see our adjacency lists get the right values. So in our adjacency list, UCLA maps to an array list with Stanford, and Stanford maps to an array list with UCLA. And I'm going to skip over a few of these actually, just so we can see a map with, should I skip over all of them? Let me skip over a bunch. So I'm going to click step over, and if you want to skip a lot of lines like this is, by the way, I'm just doing debugger tips and tricks at this point. If you want to skip a lot of lines, you can set another breakpoint. You can have as many breakpoints as you want. So I'll set another breakpoint and then click the resume button. That's going to continue execution of my program until it hits another breakpoint. It's the same as running the debugger in the first place. Run your code till you hit a breakpoint. So I'll resume, runs my code, hits this breakpoint, and it stops again and says, okay, here's all the information at this point in time. And here our adjacency list is pretty full here. We got 12 key value pairs. We can look at all of the neighbors, like Utah has neighbors SRI, SDC, MIT. Actually, let's get all the way to the end just in case we're missing a few. So Utah has those neighbors SRI, SDC, MIT. If we go to Carnegie, the starting node of our breadth first search, we have Case and Harvard, like we'd expect. Lincoln has neighbors MIT and Case. Which one am I looking for? Stanford, UCLA, and SRI. I think I'm looking for UCLA. Yeah, UCLA, Stanford, SRI, UCSB, and Rand. UCLA was the top node, right? I don't know how I'm forgetting that. But it has all the information that we want. So for running breadth first search, this is the data that we have to work with. You're going to have an instance of a graph that you're going to call add edge to get all your edges in there for all of your actors. And then you're going to have this adjacency list. And you're going to ask your adjacency list a bunch of questions. Adjacency list, what are the neighbors of Utah? Adjacency list, what are the neighbors of Harvard? Adjacency list, what are the neighbors of Rand? So you're going to say graph.adjacencylist.get Rand, and it's going to return an array list with these 4 values. And that's how you're going to run your breadth first search, is by calling that adjacency list and getting the values that you want from it. Now, of course, it'll be .get adjacency list, because in our graph class, you're not going to be in the graph class, you're going to be in your degrees of separation class, so you can't access this private instance variable, but there is a somewhere in here. Do I not even have it in this code? Oh no. Oh, here it is. A get adjacency list. So you do have a getter method for that, so you can get the adjacency list and then access all that information. Which, by the way, we have private instance variables, so you can't mess with the instance variables. So you can't change this reference. But since the getter returns a reference, you actually can modify the contents of that hash map. So something to keep in mind throughout your programming career. If you have a getter that returns a reference, whoever calls that getter can still go over to the heap and mess with your stuff. They just can't change the reference that's stored in your variables. So they can't replace this with a completely different hash map, but they can still go to your hash map and modify changes. So the getters don't protect us from that. If you do want protection from that, don't write a getter like this. You would write separate methods like add, get neighbors of a particular node and have it return the array list or even a copy of that array list if you're really concerned with people messing with your data. Or just give them like an R connector. Well, that wouldn't really work. But give them a number of that would be awkward. But something to be careful, something to think of. If you don't want to make sure nobody messes with your data, don't give them access to your data by reference. Do we want to do most incoming edges? I don't know if that would be helpful for your homework. Maybe it would be. Would it be? It's really not close to breadth research. I'll just talk through it. So with most incoming edges, this is a method that's going to find which node in the graph has the most incoming edges. So if we want to find the most outgoing edges, that's easy enough. It's the one with the longest adjacency list. But here we want to do something quite a bit different. We want to find the most incoming edges. And this is thinking of a directional graph where, as opposed to bidirectional, where each edge can be traveled in both directions, like our actors in the homework, and like the internet example. This is thinking more like the airport example, where the edges only go in one direction. So how would we find the most incoming edges? For that, we have to go through our whole adjacency list and count the number of times that node appears as the destination, as the 2 of an edge. So we're going to go through all of the adjacency list every array list in there. So we're going through just the values of the hash map. We don't actually care about the keys. We don't care about what node we're coming from. We just care about the incoming, the destination of each edge. So we're counting the number of times that a node is a destination. We're going to store that value. Man, that pop-ups drive me nuts. We're going to store that value in this hash map. This hash map is going to count how many times we've found an edge that's incoming to this node. So we're going to go through our entire adjacency list, every array list in our adjacency list, iterate over all of the values in that array list, which are all the destinations from a particular node. And then we're going to lazily initialize our hash map here if we have not seen... Why does this feel backwards to me? Oh, yeah, I see. So if we have not seen this node yet, we're going to put it into our hash map with the value 1. If we have seen it before, we're going to put it into our hash map just the same, but we can't have duplicate keys. It's already in there and we're putting it again, so we're overwriting the value at this key. And what value we're going to overwrite is whatever value was there. So we're going to get a value from the hash map, the value we're about to overwrite, and bump it up by 1. So we've seen it 1 additional times. We're going to count that by incrementing the value stored in this hash map. So this code is going to leave us with a hash map with all of the counts. For each node, this is how many times that we've seen it as having an incoming connection. This is how many times it's the destination of an edge, or how many incoming connections that node has. So what's left is to find which node has the maximum number of incoming connections. So we have our standard maximum setup. We're going to initialize max to -1, initializing max to something that's not going to interfere with our calculations is very important. We want to make sure this is -1 or something less than 0, because that's not going to interfere with our calculations. We could have a situation where we're going through a graph with 0 edges, and the max might be 0. So we want to make sure we're less than 0. -1 is the first number less than 0, so we'd stick with that. And then we could have some extra check, like if this returns -1, then we know that something went wrong, or we have an empty graph. So we can use that as an indicator that there was an error. Where if it's 0, we might have a node with 0 incoming edges is the most incoming edges, because we have a completely disjoint graph. We can also check, I guess, if the method returns null. But if max is -1, we might want to return something. I guess null would work here. Depends on what the code is expecting that's calling this code. So choosing that is important. This I forget what happens with max key in task 1. Is that what it's called, max key? Where you have a hash map where you want to find the value mapping to the largest key, and then what some students do is either initialize to -1 or 0 and find the maximum value, and then I have an incorrect solution where a test case. I'm trying to remember back. It wasn't that long ago, but it feels like forever. I have either a test case or an incorrect solution where all the values are negative. So all the values are negative, and the maximum value is like -5 or something. And students who are initializing their max to -1 or 0 get all tripped up on that. So choosing what to initialize this with that's not going to interfere with your calculation is very important. And I throw that at you on task 1 because that is, of course, a 115 concept. In 115, you talked about min, max, and how to initialize this. So I just throw that at you out the gate. But I do see that mistake every semester. But that's a 115 mistake. I don't know why I'm still talking about it at the end of 116. You all know that. So we're going to go through our incoming hash map that we just created, and we're going to do a basic max. If grab the number of times we've seen this as an incoming edge. If it's greater than max, update both values are max. This is now the maximum that we've seen. And the node, I do see this mistake on homework 1 as well. Homework 1's meant to be a review of 115, but update both values. So remember the value that you've seen, the max value you've seen, and also where that value came from, because that's what you ultimately have to return. But you need to keep track of the max so you can check this conditional to see if the next value you look at is going to be a new max. And return it. So the big thing here is that we're accessing our adjacency list to be able to get the information we need, and then using that information to do whatever we want to do. So in your homework, it's going to be accessing that adjacency list, which you'll be outside of the graph class. So it'll be something like graph.get adjacency list dot, whatever. And then use that information in the adjacency list to get the job done of degrees of separation. So I suppose we can see that in action. I'm going to set a breakpoint and then use my resume. The debugger was already running for the other example, so I just resumed. It got through all this stuff. I'm sure it printed a whole bunch of stuff to the screen. And now we built a graph. We checked for some valid paths, and now we're about to do most incoming edges. So we have this graph, just similar to the one we just saw in the memory diagram. We have 4 airports with some connecting flights. And we want to know which airport has the most incoming flights. If we look at the data, we can tell. Actually, let's look at it in the debugger. It'll be more interesting. We can tell, let's see, WDC, Toronto, Buffalo, JFK, Buffalo, Buffalo. So it looks like Buffalo has 3 incoming flights, which beats out any of the other ones. So Buffalo is going to have the most incoming flights. So we expect this to return Buffalo. So let's get into the method. See if it's going to do that. We're going to initialize our hash map for all the incoming edges. We're going to iterate through the adjacency list values. So this .adjacency list .values is going to be all of the 4 array lists one at a time. So the first array list we get, destinations. First array list we get is WDC in Toronto, which happens to be Buffalo's array list. And then iterate over these 2 strings. And then since we haven't seen these before, we're going to initialize them in our incoming hash map to 1 each. So now our incoming has those 2 values map into 1. We're going to get to our next array list, which is going to be Toronto and WDC. Oops. No. WDC and Toronto. Well, it happens to be the same thing. Iterate over. Yeah, I thought something was weird there. Yeah, we didn't get to the next one yet. So our next one is going to be an array list with just Buffalo. We haven't seen Buffalo yet, so initialize that in our incoming. We're going to get to our next array list, which is JFK and Buffalo. So JFK is a new one. We're going to add, initialize it. Now we're on Buffalo. Now our incoming does contain Buffalo already. So we're going to get the value 1, add 1 to it, and then put into this map Buffalo 2, which is going to overwrite what we have here. Let's step over so we don't get into Java stuff. So now Buffalo has the value 2. It got the value of 1, added 1 to it, and then put it back in the map as 2. Get to our next destinations, Buffalo again. We're going to do the same thing. Oops, I got into Java code, so I did step out. And now Buffalo is going to have the value 3. We bumped it up by 1 again. And we have, and we went through all 4 array lists, and now we have all that information distilled into one hash map. Buffalo has 3 incoming. Toronto, WDC, and JFK all have 1. And we run through our min code, which I'm going to skip a lot of this. We're going to go through each one. We already found Buffalo. So max is 3, best is Buffalo. And then all the other nodes aren't going to have any effect because their count is going to be 1, which is not greater than 3. And we return and print BUF. All right, so there's some graph examples. Hopefully you're getting pretty comfortable, pretty familiar with how graphs work. And we're at 129. I don't have my phone, so my alarm's not even going to go off. Not in audible range. But that is the end of lecture. That's the end of the last bit of content. So on Tuesday, just a reminder, it's going to be the quiz as usual. Send out the email at 11. And then my plan is to go through these week 11 things. Well, one, if people have questions, I'm going to prioritize questions because the whole point is to help you with homework. But if nobody has questions, by default, I'm going to go through these. This is intentionally broken code, 6 examples of intentionally broken code with tests that fail. So this test should fail. And then I'll run the debugger and find the errors and then walk you through how I would do a debug session. All right, and that's it. I'll take a quick break and go to office hours as usual. I'll either see you there or see you on Tuesday. And good luck on the quiz. Good luck finishing up the tasks.